So what's happening is we're going to have our first test. Just to remind you again, that's going to be on Tuesday. That's the 29th. We're going to cover chapters 1 through 5. Wherever we finish today, that's where we're going to stop in 5. If you were in section 990 and you told me Johnson City, you're going to Wharf Pickle. 517. If you told me Kingsport, we only have one room and it's 232 is where we're at. There's only one building here. What you needed to bring was an ID. Yeah, I know I said your ETSU ID the other day. I'll settle for any ID. You need to bring those tables and formulas that you printed out of D2L. There's 6 pages. You don't need them all, but you can bring all 6. And then you're going to need a calculator. We don't like your cell phone as a calculator. Actually, one of the things I'm going to ask you on Tuesday is put your cell phone away. Okay? That's all the stuff I can think of for the test. The test has got 40 questions on it. Multiple choice every question. There's an A, B, C, and D. I don't do all of the above or none of the above. The answer's sitting there looking at you. All right? Now, here's a couple things to remember about the test is, look, you never calculate a standard deviation without the use of Minitab. You're not going to have Minitab on Tuesday. So if I want you to say something about the standard deviation and work with it, I give it to you. Same thing with this correlation out of Chapter 4. We never calculated that by hand. If I want you to see some scatter plot and see the correlation for it, I'll give you the scatter plot and I'll give you the correlation for it. And the part we're getting ready to do tonight is that regression line. I'm never going to calculate that by hand. If I want you to work with the regression line on Tuesday, I will hand that to you on the test. Okay? The kind of things you need to be able to calculate is mean, small set of data, 5-number summary, things like that. Okay? My other thought about this test is I've got in D2L, they're not there yet because I didn't know how far we were going to get. In D2L, under content, syllabus, you'll see something called Thoughts for Test 1. What I've done is I went through each chapter and told you what you need to be able to do, what you need to be looking at. I didn't give you any specific problems to look at, but I'm telling you what kind of things I think. Look, here's what I do. I sit that down next to me and I start making the test. Right? I need a question that says, does this. I need a question that does this. All right? It's not up yet. I was waiting to finish. This will be up before I leave here tonight. Of course, that might be 10:30, but it will be up tonight. Okay? The other things is this. I was told yesterday, I got an email to remind you about the class survey. Remember, there's a link in D2L under class survey. This is due on Friday, the 25th, which is tomorrow, and I think I had it set to where things would last till 11:30. If you've already done it, we appreciate that. I appreciate that. If you haven't done it, I would appreciate it if you would. Okay? And then, as far as the homeworks go, the solutions, or the homework 3 solutions, right, the one you're going to get back tonight, the one you gave me on Tuesday, will show up in D2L underneath the content, the homework, the same place the other 2 did. It'll show up tonight at 7 p.m. And then the homework you just gave me, I want you to see the solutions to that. It's going to show up tomorrow at 11:30 a.m. And then that makes us all even for homework solutions, right? We've had 4. That's the 4 you've got. So you've seen everything that you've turned into me, even though you won't get that homework 4 back before the test. All right? If things work out good, I'll have it graded for you for Tuesday. We'll take the whole time on Tuesday. All right? We'll take the whole hour and 20 minutes. That's plenty of time for 40 questions here. All right? The warning is not all the questions, not all 40 questions are out of Chapter 3. Remember, there's still stuff about, like, what do you see in the histogram? Is this histogram skewed to the right, skewed to the left, roughly symmetric, things like that, right? Yeah, don't freak out on Chapter 3 that, like, you're going to see 40 questions out of Chapter 3. That's not going to happen. At the most, you'll see 3 or 4, right? Because I'm thinking about the style of questions that came out of Chapter 3. Now, what I want to work on tonight is this Chapter 5. We were talking about regression. So, the one we were looking at, and the one I ended up with on Tuesday, is this. It was example 5.1 and example 5.2, and that was the one where we were talking about weight gain. We talked about the NEA change, right? The non-exercise activity change. People fidget and stuff when you overfeed them. That was measured in calories, and then they measured their fat gain after that in like kilograms or something. And the scatter plot that we were looking at is, right, we thought NEA change might explain or influence fat gain, correct? Now, the reason I give it to you like that is because we made the NEA change your explanatory variable and the fat gain the response there, all right? And they drew in a regression line that looked like that, right? That was our regression line. They drew it in example 5.1, and they actually gave me the equation of it in 5.2. Well, what we're going to work on tonight is, this regression line is going to have a particular one we're going to use. It's going to have a formula for finding the slope and the intercept. And so what I want to do is, look, I'm on page 131 in your book, and they're going to talk about what's called the least squares regression line. That's the line we use, right? So this is always the least squares regression line. Anytime in this class somebody draws you a regression line on the scatter plot or gives you an equation of the regression line, it's always this least squares regression line. Now, here's the thing about this, all right? I'm going to come back here, and I'm going to look at one of these 16 individuals in example 5.1. Remember, there was a table on page 128. And I'm looking at the first person there, right? The one that has minus 94 NEA change and a fat gain of 4.2 kilograms. Remember, I told you anybody that was a minus, you overfeed their ass, they sit on the couch and don't do nothing, right? So what I've got is this. Down here is my minus 94, okay? And let's say up here is my 4.2. So what you see is you have that little dot there corresponding to that first subject in that little experiment they're doing here. Okay? Now, when I put the regression line on there, you understand that unless things are perfect, and what I mean is unless the correlation is plus or minus 1, when you fit this line to the data, you're not going to pass through all the points. Everybody understand that, right? You might pass through some of them, but you're never going to pass through all of them unless you've got a minus 1 or a plus 1. Remember, my correlation here was like a minus 0.7786 or something like that, all right? So that little dot we miss. Well, you see this right here? That's an error we're making, right? That's an error. If you don't like the term error, hell, that's a vertical distance the point is from the line. It turns out that the point's above the line here. Okay? And what I mean is this. You see right there? Whatever that value is that I have there, that's the value that the line is going to predict for somebody that has minus 94 NEA change. So how do I find that part in green? Remember Tuesday that we had fat gain was equal to 3.505 minus 0.0034 NEA change. Is that close? Okay? So if I want to find this value that I have there that the line is predicting for me, then I need to plug in minus 94 into your little equation here for this least squares regression line. So what I need to do is I need to say, okay, fat gain is equal to 3.505 minus 0.0034 times a minus 94. In other words, I want to know what the line is predicting for a person that has minus 94 NEA change. I know what the data is telling me the fat gain is. The data is telling me the fat gain is 4.2 kilograms. Why? That's one of your subjects here in this table, right? That's one of the people that they did this little experiment on. So, anybody got a calculator here? I need to know what this number is. You're going to take 3.05 times 0.0034 times 94. The two negatives are going to make that positive. So that fat gain turns out to be predicted by your least squares regression line. This regression line to be, what I get? 3.826? 246? I'm going to call it 3.2. That number we just found is this value right here, okay? It's this value right there. 3.2. Right? That's what the line predicted. We know that the person that's in the data set that had minus 94 had a fat gain of 4.2. Since they fit the line to the data, right, then the line is actually predicting for a person that would have minus 94, 3.2 kilograms. You understand, we made an error here, right? We actually had somebody in the data set that had that NEA change. Yep. So I'm going to do it like this. I'm going to give us another page, and I'm going to tell you we just made an error. And anytime you calculate that error, which is a vertical distance, that the point is from the line, you always take the observed response minus the predicted response. Look, here's the way I think about this part. That's from the data. That's what's observed in the data, right? You had a lady, you had a subject here that had minus 94 NEA change. This is coming from the line. And then for that particular NEA change, we plugged that into the regression line, and we got that value for the predicted, right? That's what the line is telling me we should have had. Well, what was the observed? The observed was 4.2. The predicted was 3.2. We made an error of 1 kilogram. Now, you do understand, right? There's nothing special about that first person in the data set. Could I have done that for any one of the 16? And the answer is, yeah. Would I have made an error? Yeah, I would have made an error unless the line passed through the point, and then the observed that came from the data and the predicted that came from the line would have been the same. But as long as there's some distance between a point and the line, you're going to get an error, right? So looking at what I see here with the scatter plot and the regression line, the only one that even looks like it's close to not having an error is the one all the way to the right there. It looks like the line might actually pass through that, and I'm looking at figure 5.1. The point is when we do this and we fit remember I told you, we always fit the line to the data. We never fit the data to the line. Right? You fit the line to the data. When you fit the line to the data, we make errors. Well, the deal is this. Okay? We want to use the line for prediction. Translation, I want to use the line for, you give me a value of your explanatory variable, and I want to use the line to predict the value of your response. Well, if this is the use that we have in mind, and I'm going to be honest with you, in this class, this is the use I always have in mind, is using the regression line to predict the value of y for a given value of x. If that's the case, and we're making all these little, that was almost a bad word, all these little errors, right? Vertical distances, yeah? You want to minimize those. You want to make these vertical distances as small as possible, all at the same time. Well, there's a line that does that for us. It's called the least squares regression line. That's our line in this class. It's the line we work with. It's the line we always use. And what it does is, it makes the errors as small as possible. Look, I gave you my interpretation of the least squares regression line. I'm going to read the one that says to you in the book. And I'm on page 131. There's a little box there. And it says, the least squares regression line of y on x. Now, you see that language? Y on x. Y versus x. Anytime you see on, it's always y on x. Anytime you see versus, it's always y versus x. Okay? Is the line that makes the sum of the squares of the vertical distances, the data points from the line, as small as possible. I like my interpretation better. It makes all those errors as small as possible all at one time. You've got to think about it like this. You've got the data. You've got the scatter plot. And the line is trying to be fitted. Maybe I tweak it a little bit like this. And then that makes, when I add all those errors together, they're squared. I add them all squared together, I get a smaller number, right? A little more. And then you get the perfect line that sits on there. And it makes all those errors as small as possible. It's the best fitting line. Right? It's the best fitting line. Now, here's what we need. I need an equation. Well, that's on page 132. I need the equation for the least squares regression line. The regression line that makes all those errors as small as possible all at one time. Well, we know it's going to have the following form. Now, I'm going to do that to you. And it's an A plus BX. I'm not changing the crap I wrote on Tuesday. Remember I told you the line was A plus BX? That was when we talked about straight lines in general. The different part is, you see this right here? That's read as Y hat. We have to distinguish between the values of the response variable that comes from the data, that's a Y, and the values of the response variable that come from the line. We have to distinguish between the observed Y from the data and the predicted Y that comes from the least squares regression line. Anytime you see Y hat, they're talking to you about this is a predicted. It's coming from the line. We have to distinguish it somehow, and that's how we do it. The line does not give you what is observed. It doesn't give you the data. It gives you something predicted for the response variable. Then, if you'll let me do that, we need to talk about the slope. Remember, the slope is the B. Remember, that's your rise over the run. B is given to you by the correlation, that's your R, the standard deviation of the Y over the standard deviation of the X. Remember, there's two quantitative variables here. There's the X variable and the Y variable. That's how, if we were going to calculate the slope by hand, that's how you would do it. You would need the correlation and both of the standard deviations for both of the variables. And then you have the intercept, which is our A, and it's given by, that's the mean of the y's, minus b times the mean of the x's. So you notice we can find the equation of the least squares regression line by knowing things that we have already talked about in this class, right? The things you need to know is the means, the standard deviations, and the correlation. Those are 5 things we've talked about in this class. That's the other reason we like it for this class. Not only is it the best fitting line, not only does it make those errors as small as possible, so this makes this line very good for doing prediction, is the things that actually show up in the formulas for the slope and the intercept are things we have talked about and worked with in previous chapters. That's the reason we like that. Relatively simple, right? You're looking at means and standard deviations and correlations here. Now, here's what I want to do. All right? I'm going to come over to your homework. See, because look, the next thing is using technology here. Everybody knows we're not going to do this by hand. How do I know that? Well, hell, the standard deviations and the correlations show up here. Obviously, we're not going to do this by hand. The next thing is going to be facts about the least squares regression line. But what I want to do is this. Before I get to any facts, is I want to come over here and I want to look at the problem out of your homework to show you this is what I would expect out of you if I assigned a problem like this. This is how I get the scatter plot, the regression line, and things like that. So I want to come to 5.39. I have a reason for picking that problem. 5.39, and that's on page 155 on the bottom there. I feel like this is a standard type of problem in this chapter, dealing with the regression line and how do you work with it. It says, sparrowhawk colonies. One of nature's patterns connects the percent of adult birds in a colony that returned from the previous year and the number of new adults that joined the colony. Here are data for 13 colonies of sparrowhawk. The 2 variables you have measured is the X is the percent that returned, and the Y is the number of new adults. Does that problem sound familiar to anybody? You just did that one for homework 4, right? You made a scatter plot and you calculated the correlation. Hopefully you figured out that you saw a negative association. Hopefully you figured out that the sparrowhawk was a long-lived territorial bird. Hopefully. Okay? Well, now, the reason I'm picking is because you've seen that problem. And I told you on Tuesday, chapters 4 and 5, hell, that's just one big chapter to me. What do I want to do? Oh, I want to make a scatter plot. I want to see if I see a linear form. If I do, I want to calculate the correlation. If the correlation confirms that you're seeing a linear form, like we had here, what did you get for a correlation on the homework? Wait. I got a correlation of minus 7.748. Negative association, that's pretty strong, right, at negative 0.748. So it made sense to talk about the correlation. Well, if I'm seeing a linear form, then it makes sense to want to get the regression line, right, the least squares regression line. It says, you saw in exercise 4.28 that there's a moderately strong linear relationship with correlation R equals minus 0.748, right? That's what you saw in the problem you did for me. Part A says, find the least squares regression line for predicting Y from X, for predicting the number of new adults that will join from the percent of birds that actually return to the colony in a year. Make a scatter plot and draw your line on the plot. Okay. I'm going to Minitab. Sorry. I'm not going to spend time doing it by hand. $39, wasn't it? So that's that table, right? You got 13 colonies. So here's what I want to do. For me, I know I'm going to want a scatter plot, right? I want the regression line on there, right? And I want the equation of the regression line all at the same time. So I'm going to go to stat. Now remember, you've been here when you wanted to go to basic statistics and find the mean and standard deviation, 5-number summaries, the correlations under that part. I'm going to go right here to regression. Okay, so that's a little new. I went to, what was that, stat, regression, and then what am I interested in? Look, there's a reason I use the language I use it. We're fitting the line to the data. I want a fitted line plot. I want to fit the regression line there, the least squares regression line. If I click OK here, if I click that one. Now, Minitab's actually trying to teach you as we go too. You see where it says response variable y? What was the response variable? The response variable is the number of new birds. Now you notice for the x, they didn't call it the explanatory variable anymore, did they? Do you know why Minitab calls it the predictor? They know why you want the equation of the line. You want the equation of the line is because you want to use it to make a prediction, right? That's exactly what you want. It's trying to tell you that. Look, I know why you want the line. You want the line so that you can actually take a value of your explanatory variable and predict the value of your response. So that's the predictor variable. Hell, it's still the explanatory variable. Okay? And that was the percent return. Now, you see the type of regression model? Don't screw with that. It's always linear, and we're always dealing with linear, right? We're interested in the least squares regression line. I'm going to click OK here. All right? Now, folks, in case you don't know, it gave me the scatter plot. That red line is the least squares regression line. Does everybody see right under where it says fitted line plot? That's the equation of your least squares regression line. The number of new birds is equal to 31.93 minus 3.04% return. That's just like the one in example 5.2 about the NEA change in fat gain. It gave that to me. Now, what I'm going to do is I'm going to come back here, and I'm going to write down that for this problem, we made the scatter plot, okay? And the regression line is at the top there. The regression line's on the scatter plot, and it's the new birds. Now, I got to put a little hat, right? That's your Y. I want to get it stuck in your head that this is what the values are going to be predicted by your line. And what was it, 31.09 or something like that? 31.93 minus 0.304%. What the hell's the return? Look, the reason I keep going back and forth is because I'm just reading what was on the top there. So it gave me my least squares regression line. It gave me the equation, right? So that you know this is the least squares. That's what Minitab gives us. Okay? That's what Part A asked me to do. It asked me to find a scatter plot, put the line on there, find the equation of the least squares regression line, and that all did that. One more time. Right? It's fitted line plot. I went to stat regression, fitted line plot. I told it the y and the x. And when I did that, it came up right underneath the fitted line plot. That's your equation of your line. It don't put the little hat on it. It expects you to know that you're using this for prediction, and these are going to be predicted values for new birds. All right? So, Part B says, explain in words what the slope of the regression line tells us. Well, here's my question is, I see two numbers there. I see 31.93 and I see a minus 0.304. Which one's the slope and which one's the intercept? Which one's the A and which one's the B? B, I'm going to put it in words here. The slope, remember, is your B, and that's the minus 0.304. Remember, you take the sign. Since it's negative, the slope is negative. is the line got the right tilt to it for it to be negative? It's tilted backwards, right? Lines like that have a negative slope. You have a negative association, negative relationship, right? That's your direction. Okay? Now, when it says, explain in words what the slope of the regression line tells us, it means, would you please interpret the slope here? Now, we did that on Tuesday. I only did one problem like that. Remember, you're going to increase your explanatory variable by 1 unit, and then you're going to tell me how the response variable changes when you do that. So, for each additional now, what's your explanatory variable? It's the percent return, right? So for each additional percent of returning birds. Now, obviously, I got to write it out in words. The explanatory variable is the percent of returning birds. So you're going to increase that by 1. So for each additional percent of returning birds, the number of new birds that join the colony, that's your response variable, right? Does it increase or decrease? Remember, the sign of the slope will tell you whether it increases by that number or it decreases. The slope is negative, so the number of new birds that join the colony decreases by 0.304. I don't have to write the negative because decreasing is telling me it's negative. Decreases by 0.304 birds on the average. I increased your explanatory variable by 1 unit. The response variable in this case is going to decrease by the slope on the average. If you'll go back and look at Tuesday, I wrote the same style of thing about the NEA change and the fat gain. Okay? Now, there's a part C. But here's what bothers me. All right? How come they didn't ask me to interpret this intercept? We had that talk on Tuesday. I told you, you can always explain in words or you can always interpret the slope. Nobody cares. You always can do that. But you won't always interpret. You won't always tell me anything about the intercept. Now, the one about NEA change and fat gain, I could. Because remember, for the explanatory variable, I had some that were negative and I had some that was positive, and 0 was in the data, right? 0 was in that range. Well, let's back up for a second here. You see where it says percent return? It ranges from 40 up to 80. Is 0 in there? No. So when 0's not in that range of data, you do not want to start telling me about the y-intercept. Well, hell, think about what the y-intercept is here. You have 0% of birds returning from the previous year. Hell, you ain't got a colony. Let alone the number of new birds during what? That spot? It doesn't make any sense, right? You don't want to, you're at 40 is the smallest. You don't want to tell me nothing about what's happening at 0. Actually, 0 don't even make any sense here. Right? 0% of the birds returned to, I mean, I ain't got nobody. How do, no, I wanted to point that out to you because I told you that on Tuesday. With the NEA change and fat gain, I interpret them both. Here, I can interpret the slope always. Y-intercept, it don't even make any sense. Okay? Okay. Now, we can go to part C. Because part C is the other thing we want to be able to do here. All right? An ecologist uses the line based on 13 colonies, right? The line was fit to those 13 data points, those 13 colonies, to predict how many new birds will join another colony to which 60% of the adults from the previous year return. So we want to predict new birds when 60% return. Now, you can go back and look at the data set. There is no colony in the data set. I take that back. There is one. It's the third from the last. Right? But they're wanting me to use the line to predict the number of new birds that are going to join the colony when 60% return from the previous year. As soon as I see this, what they're telling me is, and look, I got to give it to you as a math guy. All the problems always give it to you written out like that. What I'm asking you to do is, I want you to find I'm going to put the little hat on because I want you to know we're using the line. When X is 60%. Right? So that's what it's asking for. So we've got our equation. The new birds, right, with the little hat on his head is 31.93 minus 0.304 times, remember, things are actually in terms of percent. We're not going to change it. You're going to use the 60. You're going to plug 60 in for the percent returning because we want to know how many new birds are predicted by your line. So you're going to pull out the calculator. You're going to take 31.93. You're going to subtract off 0.034 times 60. Tyler, what'd you get? What was it? 2.04. Total? Yeah, and then subtract that from 31.93, please. I want the prediction. 29.89. So what the line is doing is, what'd you get?
I got 13.69.
Try again. Okay. So the line is predicting 13.69 birds to join the colony if 90% of the birds return from the previous year. Okay. That's what the line is predicting for us. Now, was there anything special about 60%? I mean, I know the problem asked for 60. Could I have done 45? Could I have done 50? 52? 57? Could I have done any percent between 40 and 80 and we'd have been happy? Yeah, that's what you use, right? You were between 40 and 80 on the percent returning. I could have picked any number. They just picked 60. I mean, we could have picked 65, 61, whatever. What do? Well, I mean, I got the equation in the line. I just plug in. Yeah? And we go at it like that. That's the way the problems work. Now, the reason I picked that one from your homework, twofold. You'd already seen the problem. I built on that problem from the one you did for homework. And if you want to see a style of problem that's going to show up on Tuesday with the regression line and everything, it's that right there. Now, I'm not telling you I don't know what two quantitative variables I'm going to come up with, right? But what I'm going to do is I'm going to give you a setup. I'm going to give you a graph that looks like that with the least squares regression line on there. And I might throw R in the part up here too. Then I want to ask you some questions, right? Can you interpret the slope? What's the interpretation of the slope? Like that. Can you use it to make a prediction? In other words, if your X is this, what's your predicted Y? Which is what we did here. That's the reason I did that problem. Because out of everything that we've done in Chapter 5, that's where we're at. This is how the problems come to. This is where we end up at. All right? Now, I know I still got to talk to you about facts about the regression line. All right? Tyler, do you remember what I was going to ask you? Remember the manatee data that I could never find, and you told me you found it in Chapter 5? Do you remember what problem that was? Okay. Folks, I didn't forget about you folks in Johnson City. But here's what I want to do. Back in Chapter 4, there was a problem where they made a scatter plot. And it was like the number of boats registered and the number of manatees that were killed, right? And I couldn't find the data back there. But then the data actually shows up in 515 on page 147. So here's what I want to do. All right? I want to get that data. I want to make the scatter plot of it. I want to put the regression line on there. I want to get the equation. All right? Well, I mean, look at 515. Table 4.1 gives 37 years of data on boats registered in Florida and manatees killed by boats. Figure 4.2 on page 108 shows a strong positive linear relationship. The correlation was R was equal to 0.954. We'll calculate that for us. The problem says, find the equation of the least squares regression line for predicting manatees from thousands of boats registered. Because the linear pattern is so strong, we expect the predictions from this line to be quite accurate. Well, once you see how good the line fits the data, we're expecting things to be really accurate. Here's what I want to do. All right? I have two reasons for doing this. One is it pissed me off I couldn't find the data before. And two, I wanted something that was positive. Now, look, that's nothing more than that data back in Chapter 4 for that scatter plot, right? So what I want to do is I want to do what I just did for the ones about the percent returning and the number of new birds, if that's okay with everybody. So I'm going to go to Stat, Regression, right? Anytime I want the regression line and the line on the scatter plot, that's where I go because I want it all at one time. If I go to Fitted Line Plot, now, what was we trying to do? We're trying to use a number of boats registered to predict the number of manatees killed, right? Number of manatees killed was the response variable. The number of boats registered is your explanatory. So I want the number of manatees killed and then the number of boats, right? So I'm going to click OK. Now, you do understand that that line fits the data better than the one from before. Remember, this correlation they just told me was was 0.954. Is that really close to 1? So you have a very strong positive linear relationship here. Everybody understand that? In other words, as the number of boats registered increases, what happens to the number of manatees killed? It increased also, right? This is closer to 1 at 0.954 than the one about the sparrowhawk and the percent returning and the number of new birds. That was negative 0.748. This one's closer to 1 than that one was to -1. They give me the equation of the line, right? Fitted line plot. It's right there at the top. So I'm going to do this. I guess we could think about this as being problem 515. My version of it. Okay. My regression line looks like minus kills is equal to minus 44.83. That seems like kind of a bad way to put it. It's like we target practice on the manatees or something. All right? Is equal to minus 44.83 plus 0.1323. And that must be the number of boats. Okay? Now, I'm going to treat this just like I did the last problem. Right? There's your least squares regression line. We want to interpret the slope. So, I know the slope is B is equal to 0.1323. You notice it's plus 1.323. You saw a positive association. I see a positive slope in my line. It follows the association, right? I want to interpret that. So we're supposed to increase our explanatory variable by 1 unit. The explanatory variable here is the number of boats registered. So for each additional boat registered, I'm hoping you understand I just increased your explanatory variable by 1 unit. You're looking at the number of boats registered. For each additional boat registered, the number of manatees killed, does it increase or decrease this time? The slope is positive, right? So it's going to increase by 0.1323 manatees on the average. So there is where we've interpreted the slope, where the slope is positive. I'm going to underline this. It increases. Why? This is a positive slope. It will decrease if the slope is negative. So for each additional boat registered, the number of manatees killed increases by 0.1323, whatever the value of the slope is, manatees on the average. I don't think they'd ask me to do that. Suppose we expect the number of boats registered in Florida will be 890,000 in 2014. What would you predict the number of manatees killed by boats to be if there are 890,000 boats registered? Well, when I look at this, okay, you understand that they've rounded this off, right? The number of boats is in terms of thousands. Yeah? So if they're talking about making a prediction when you're looking at 890,000 boats, what number am I looking at here? I'm looking at it being 890. Remember, the data is given to you in terms of the number of manatees killed, straight up number. The number of boats registered in terms of thousands of boats registered. So what that means is you need to chop off the last 3 zeros there. So what they want me to do is they want me to predict, and I'm going to use their language, kills when X is 890, which stands for 890,000 boats registered in whatever year they're talking about here, 2014. So you're going to take your line, okay? You're going to look at the number of kills predicted. What was it? Minus 44.83 plus 0.1323 times 890. So now we're back to the calculator again. We're going to predict the number of manatees killed for 890,000 boats registered. Does everybody understand what I did here? Why the books asked me about 890,000, why I'm using 890? Because it's in thousands, right? That's the way the data was recorded. And when you see 890, that means 890,000. It's in thousands of boats. So I'm going to get here. What do you get this time, Tyler? 9. I'm going to go to 9 manatees. So the line is predicting 72.9 manatees to be killed if there are 890,000 boats registered. Okay? It also says, what would you predict the number of manatees killed by boats? We predict 72.9. Now look, we all know you can't kill 72.9. The line's giving you an exact answer, right? I'm assuming it's between 72 or 73. Yeah? 72.9 is what the line's predicting there. It says, Explain why we can trust this prediction. Why would you trust this? Oh, here's my deal. You see this one? I trust it. How good does the line fit the data there? Yeah. You understand that the line fits the data better here than in the last one, correct? I trust this prediction more than I trusted the prediction about the sparrowhawks. Why? The line fit the data better here than it fit here. Is the correlation telling you that? The correlation here is a 0.954. There's your line. The points are smashed on it. The other one was minus 7.748. There was a little more spread there, right? The line wasn't as accurate. Here the line is more accurate. Why do I trust it? Look, in real world, they don't get no better than this. As long as I'm predicting between 450 and 1050 here, you understand I'm looking at this parts here, yep? Okay? I feel really good. I actually really trust it. The line fits really well here. Okay? Part C says, predict the manatee's deaths if there were no boats registered in Florida. You know what they're asking you about? They're asking you about the y-intercept here. Remember, that's when x is 0. When there are no boats registered in Florida is when x is 0. So that part, we want to predict kills when x is 0. It says, explain why the predicted count of deaths is impossible. We use x equals 0 to find the intercept of the regression line, but unless the explanatory variable x values takes values near 0, predict for x equals 0 in this example it has a name. Outside that range of x values, we don't do that. What happens when you plug 0 in here? In other words, what's the y-intercept? The intercept is your a, right? And if you'll look, your a is minus 44.83. Sorry. Minus 44.83, correct? Minus 44.83. Well, there's some magic going to happen if we don't have any boats registered. Okay? We predict minus 44.83 manatees killed for no boats registered. I don't know what the hell minus 44.83 manatees means. If we don't have any boats registered, are we making manatees? You understand. The problem here is you can plug any x value into the least squares regression line you want. There's nothing stopping you. Hell, that's just like an equation you just saw in college algebra. The problem is right here. You see where we go. Now, I'm looking at the x-axis here. I'm looking at values of your explanatory variable. You see they range from 450 up to like 1,050, right? Yeah? Is 0 close to that? No. Do not do this. Do not try to interpret the y-intercept. Do not try to tell me what's happening when your explanatory variable takes a value of 0 unless the scatter plot you're looking at has values of the explanatory variable close to 0. 450 is not close to 0. Now look, we've done 3 of these problems. We did the NEA change in fat gain. We interpreted the y-intercept there, right, because I had things that were actually negative and positive. 0 was there. We did the one about percent returning and the number of new birds. We didn't have anything close to 0. The book didn't ask you to interpret it. Why? Because you can't. It makes no sense. And then here, the manatees and the manatee kills and the number of boats registered, right? They actually asked you to predict when x is equal to 0 so you could see that this is a bad idea. you're getting something crazy here like a minus 44.83 manatees. That don't even make any sense. And the reason is because you're trying to predict outside that range. We don't do that. All right? Now, you notice I've done the same thing 3 different times for you. The problem from Tuesday, the one about the sparrowhawks, and the one about the manatees. What did I do? I showed you how to get the least squares regression equation, right? Put it on the scatter plot, how to interpret the slope, how to interpret the y-intercept when it makes sense, how to make a prediction. That's what's happening here. Okay? That's what we need to be able to do. And then what I would like to finish up with here is there are some facts that we need to pay attention to, and they start on page 135. Okay? Look, it's just like the standard deviation and the correlation. If we're not going to calculate things by hand, there has to be little facts that we know about also. And the facts for these are facts, and they're about the least squares regression line. Look, I'm bad about saying the least squares line, or I'm bad about saying the regression line, and whenever I say those things in this class, we're talking about the least squares regression line. All right? The first one is the distinction between explanatory and response variables. It makes a difference. It may not look like it made a difference in your scatter plot, but it'll make a difference in your regression line. It makes a difference. Now, the reason this shows up as number 1 is because the correlation doesn't care. The correlation wants you to have 2 quantitative variables. It doesn't care if you had an explanatory response. The least squares regression line, it cares. It cares so much that I'm going to do this to you. You see that one right there where the number of boats registered is your explanatory variable and the number of kills is your response, and we wrote down what the regression line was? Well, let's go back here and do this all over again. Now, I'm going to give you, you're not going to see much difference in your scatter plot. It'll look the same to you, but look at the regression line equation. So I want to put in boats as the response and the kills as the predictor. In other words, what I just do, I just change your explanatory and response variables. I changed your x and y. When I click OK here, that's the one we just got. So now the kills is your x variable. The number of boats registered is your y. Does the 2 lines look different? Well, hell yes. You change the y and the x. Right? I understand that the scatter plot looks similar, but you've got to remember, you're seeing this positive association. You're going to see it in both. You don't get the same regression line. You don't get the same equation for the least squares regression line. That's the reason why it makes a difference which one's the explanatory and which one is the response. You flip-flop them, you get something completely out of the ballpark. Not even close to making any sense. Right? That's what we got there. I wanted to show that to you. Number 2. Right? What I would like to do is I'd like to look at this part right here. Remember, this is the equation I gave you for the slope of the least squares regression line. The correlation times the standard deviation of the y's over the standard deviation of x's. Okay? Now, my first thought is this. Is the slope and correlation have the same sign. If the correlation is negative, it's telling you you're seeing a negative association. Your least squares regression line is going to have a negative slope, right? It has to match that direction. If the correlation is positive, that means you see a positive association, and the slope is going to be positive to follow that positive relationship, that positive association. Right? So the correlation and the slope will always have the exact same sign. Hey, anybody remember anything about the standard deviation? What possible values can your standard deviation take? Can the standard deviation ever be negative? It's always bigger than or equal to 0, correct? So the sign of the slope is coming from the sign of the correlation. They match. Correlation's positive, slope's positive. Correlation's negative, slope's negative. I'm going to give you like that's little part A. Then there's a little part B here. Okay? A change in one standard deviation in X corresponds to a change of R standard deviations in Y. It's not a one-for-one. Okay? You know, if you change... Look, when we interpret the slope, right, I'm always about changing the explanatory variable by 1 and then seeing how the response variable changes, right? What I'm telling you here is looking at that equation that R times the standard deviation of the Y's or the standard deviation of X. If you go down here and you change by 1 standard deviation in the X, it doesn't change you by 1 standard deviation in the Y's. It only changes you by R times that, R standard deviations. You understand that's less than 1 because R is between minus 1 and 1. It's not a one-for-one change. You might change this far down here. You're not going to change that far. You're not going to change 1 standard deviation. It's going to be less than 1 standard deviation. Has anybody ever heard the term regress to the mean? Things go back to the averages. How about it that way? Right? Things always tend to come back to what the average is. That's what the hell's going on here. Things will get back to what the average is. Why? Because it's not a one-for-one change. It's a 1 change down here in standard deviation. It's less than 1 up here. It's R times that up there. Okay? Now, if I got to pick which ones are, I like that one. The slope and the correlation have the same sign. I give you that. The book tells you that. All right? 3. And I'm just going to throw 3 out there. You understand, somewhere on your scatter plot, there's the point of the mean of the x's and the mean of the y's, right? There's that point there. It may not be a dot, but there's that value there. That point is on the line. What I mean is this. Let's say this is the mean of the x's and that's the mean of the y. You come out here and you would make that point x bar, y bar. The line passes through it. I don't care if it's a negative slope or if it's a positive slope. The line, the least squares regression line, always passes through that one particular point. We know that for a fact. Okay? Now look, I always think about why I should throw that one out there to you. Oh, it's an interesting fact. Shit. If I had to graph it by hand, when I go to graph the line by hand, how many points do I need? I already know one of them. I ain't graphing nothing by hand. It's an interesting fact. Okay? Now, I'm going to be honest with you. Out of the 4 here, right, there's 3 and there's a 4th one. Out of the 4, I think number 4 is probably our most important little fact here. This is going to show up. All right? And what we're going to do is, I'm going to do it like this. The square of the correlation, you know, little r, so you take the correlation and you square it. Now, when we do that, normally the correlation runs between -1 and 1. You square it, and now you're between 0 and 1. You've made it everything positive here. Look, I'm going to write it word for word out of the book here, and then I'm going to give my spin on it for you. Is the fraction remember, it's a number between 0 and 1. Hell, it's a fraction, right? Is the fraction of variation in y that is explained by the regression line. Now, that's quoted right out of the book. All right? Okay. So what happens is, this is what we do. We take the correlation and we square it. We get a number between 0 and 1. All right? We turn that into a percentage. We move the decimal place 2 to the right. And then you start talking to me about the percentage of variation in the response variable y that is explained by the regression line. Now, I'm going to give you, look, you know, I always try to tell you what the book tells you in case you read. And then I give you my take on it. What the correlation squared is telling us, it tells us how successful we were at explaining the linear relationship. Right? And I think about it in terms of that percentage. Your percentage is going to range from, if you don't mind, I was going to do this. Let's say I give myself a little line here. This little r squared, when I turn it into a percentage, when I move it 2 decimal places to the right, it's a number between 0% and 100%. Right? Now, when I go this direction, how'd we do? Line fits well. The closer I am to 100%, the better the line fits. As I go this direction, line doesn't fit. The closer I get to 100%, the better the line fits the data. The closer I get to 0, the line doesn't fit the data. So, do you remember this little problem we did 515 about the manatees? And we made that prediction for 890,000 registered votes, and we plugged in the 890, and we got whatever it was, 72.9 manatees killed. And it asked us, just to quote it, 515 said, explain why we trust this prediction. Well, first off, your correlation was a 0.95 something. When you square that, what did you get? Okay. Here's how important this little r squared is. Okay? I'm back to that. Okay? Now, does everybody see the scatter plot? You see the fitted line plot, you see the equation of line. You see the little box over here to the right-hand side? Does anybody see where it says r squared? And it gives us r squared as 90.9%? Yeah? It gave it to you, right? So for the one about the manatees, we had R squared is 90.9%. How do you feel about making predictions with that line? I feel damn good. I'll predict like a madman. I trust them all as long as I'm inside that range of values. It don't get no better than this, folks, at 90.9%. When you're looking at real life data. Now, what this means is 90.9% of the variation in manatees killed is explained by the linear relationship. That's as good as it gets. Unless you let me pick the data, you ain't going to get no better than 90.9%. The closer that number gets to 100%, the better the line fit the data, the more accurate our predictions, the more we trust them. The more the variation in your response variable that is explained by the linear relationship. Now, here's the deal. Here's what's going on with this, right? So I wanted to give you one where this is how you do this, right? And I've just taken that thing I quoted out of the book. Instead of saying fraction, I put the percentage in there, and it's the 90.9% of the variation in manatees killed. Your response variable, your y, is explained by the linear relationship, by fitting the line on there. Now, I'm going to come back here for a second, and I'm going to scream at you about this for like 3 minutes. You see that scatter plot? Look at your y variable, right? You understand that we have different y variable values of the y variable here, right? For different number of boats registered, you have different number of manatees killed. They're not all the same value, right? We didn't kill 50 of them every year, right? It moves, right? The value of the number of kills, the response variable changes. It's showing variation. Everybody agree? It's showing spread. It has a positive standard deviation. Which word do you want? It's showing variation here. It changed as we went from one year to the next. You got a different value, yeah? That variation comes in two pieces. One comes from, you're looking at a linear relationship. You got the regression line on there. As you start increasing the number of boats registered, what had to happen to the number of manatees killed? The points need to follow that linear relationship. So as you increased here, you had to increase here. That's what R squared's measuring. How much of the difference are we seeing? That variation is explained because you had a linear relationship and it had to follow that. So as you increase this one, the number of manatees killed had to increase and follow that line. That's what R squared's measuring. So with that thought, I'm going to tell you, the closer that is to 100%, the closer the line, the points lie to that line, right? Because more of the variation is explained by the linear relationship. Now, you understand, you see the scatter of the points about the line? That's the rest of it. That's not because of the linear relationship. That's just because we're not perfectly linear, right? So if 90.9% of the variation in the number of manatees killed is explained by the linear relationship, had to follow, then 9.1% of the variation comes from the spread of the points about the line. The closer R squared is to 100, the better the line fits the data. We were really successful at fitting the line to the data. Our predictions are more accurate. We trust them more. The closer it is to 0, you get me down to where your little R squared is 25%, and I don't want to make I don't trust nothing. Right? 50% and above, then I start trusting things. Under 50%, hell, that's like flipping a coin, right? Okay? Now, here's what I want to do. I screamed at you about that one. 90.9% of the variation in manatees killed is explained by the linear relationship. Good. I'm going to back up here. I deleted it, but I'm going to do this. I'd like to see those sparrowhawks again. Do you expect their R squared to be 90.9%? You expect it to be higher or lower? Oh, hell, just square the correlation, right? Fitted line plot. What was it? New birds, percent return. What's R squared? 56%. 56% in the number of new birds that join a colony is explained by the linear relationship. How good is that? My problem is 44% of the variation is the spread of the points about the line. You understand why I told you the other one was more accurate, was better. Their R squared was higher. Now, let's say I do this to you on Tuesday. Let's say I give you something like this. Right? And you can read the little R squared there is 56 point, right? So I'm going to do this. Let's say your R squared is 56.0%, which means R squared is equal to 0.56. Let's say the question asks you for we got to have the calculator out, right? We got to do this. Takes the square root of 0.56. What'd you get, Tyler? 0.75. Now the problem is, this could be plus or minus. If I show you the scatter plot, what's it got to be? What's the correlation got to be? Is it going to be positive or negative? You can say it out loud. It's okay. It's negative, right? Because on your calculator, you never see a plus or minus. If you take the square root of 0.56, you get 0.75, right? And you might think it's positive. Well, the calculator won't give you the plus or minus, but there's actually a plus or minus there. You have to look at the scatter plot to see if the correlation is negative or positive. Yeah, right? That's the reason I backed up. I wasn't just pulling this out of thin air. I come back to look. Oh, hell, I see a negative slope. I see a negative association. The correlation's got to be the negative 0.75. Yeah? Everybody clear with that? Because I've been known to give that kind of question. You know, give you the little thing and ask you, okay, what's the value of the correlation? And then you got to know, well, hell, it's got to be negative. My calculator's giving me a positive one. Well, there's a plus or minus there that the calculator won't give you. All right? Now, I would like to stop at that point. Okay? I mean, there's a couple more things we need to talk about in this chapter. We got plenty of stuff for 40 questions. So that's where I'm going to stop. Is the last thing I talked about was on page 136. I guess it's 137, right? And then that's it. And then we'll pick up on page 138 about residuals on next Thursday, right? So your test is going to go through that little R squared, making predictions, R squared. You know, can I find R from it, which is what we just talked about. Is that fair? So when you see my thoughts for test 1, remember they're going to be right here. They're under the syllabus. They'll show up tonight before I go home. Here's my thoughts for test 1. Just to show you, since I have, you guys can pack up, this is what I did. So when I say chapters 1 through 3, be able to identify the who. Who in the hell are the individuals and what are the variables? Be able to identify data, categorical, quantitative. Look, these are the things that we've done, right? And I've done over and over again. How should we describe a categorical variable? I'm telling you. How should we describe a quantitative variable? I'm telling you. Be able to describe the distribution of a quantitative variable, the description of the shape. We've done that, right? These are all the little pieces that we've done. And then where does this one end? I got to throw in the little thing there about R squared. Okay, and that's the only thing it's missing. That last part about what's the R squared telling you about that percentage of the variation. I'll have that up before I leave tonight, all right? Make sure you get your homeworks back. There's some of you got 2 coming back. I will see you on Tuesday. Be careful going to the house.